So I will talk about the valence quark and gluon TMDs for the Spin-1 system in the basis light front quantization approach, which is a light front Hamiltonian approach. And yeah, I have two parts in my talk. In first part, I will talk about the particularly TMDs and PDFs of rho meson in basis light front quantization approach. And in the second part, I will talk about the structure of deuteron in some other approach, that is light front holography approach. Okay, so this BLFQ work has been done in collaboration with in IMP and with the Professor James Berry at the Iowa State University. So first of all, I will talk about what motivates us to study the Spin-1 structure. And then I will come to the approach that we use to study the Spin-1 structure, the basis light front quantization approach that Chandan has already been talked about yesterday. And then I will show some results of TMDs of rho meson, the quark TMDs and gluon TMDs. And then I will show some PDFs that are the collinear limits of TMDs. And then I will show some results of deuteron which we have just produced last night. So yeah, then I will conclude my talk. So why rho meson is so important to study? Rho meson carries a nuclear force, as we all know, within the atomic nuclei, and the pyro mass splitting is very important since they have the same quark content. So gluon dynamics is very important to study this pyro mass splitting. And there is Spin-1 structure that has like a special structure, the tensor polarized structure that cannot be found in Spin-0 or half systems. And there is some lattice data for, although there is no data for experimental data, but there is lattice data for Spin-1 system for gravitational form factors and moments of the PDFs. So, but there are some proposals to study this tensor polarized structure for the deuteron case, where JLab has been proposal has been already approved, and Fermilab proposed this in 2022, and yes, you also have potential to observe this. And yeah, this is obviously a largely unexplored field yet, as Adela mentioned, but it can, yes, open the new field of spin physics. There are some deuteron data for from Hermes, but there is a few data points. So yeah, it is difficult to conclude from that. So before going to the basis light front quantization approach, I will just introduce about some light front coordinates that we use. So this P minus is the light front Hamiltonian, P perp is the transverse momentum, and P plus is the longitudinal momentum. So we will, from the basis light front quantization, we will produce light front wave functions. Once we have the light front wave functions, we can study the three-dimensional structure and the hadron. We can study the hadron spin, how it is decomposed into the partons. So, and from that we can also study the three-dimensional structure like transverse momentum dependent distributions and GPDs. And further limit, we can also study like parton distribution functions and form factors. So this approach has already been introduced by Chandan. This is the non-perturbative approach where we solve the eigenvalue equation, and this approach is basically to solve the relativistic many-body bound state system. So this approach has successfully been implemented to the spin half and spin 0 system. So our motive is to extend this approach to the spin 1 system. So yeah, the Hamiltonian we take here is like light front Hamiltonian, light front QCD Hamiltonian, and the confining potential. So our Fock state expansion for the meson state is till now is just 2 Fock space. We expand our meson state in the up to 2 Fock states, and others are just truncated for now. Yes, our light front Hamiltonian has three terms. The kinetic energy term of quarks and gluons, since we have gluon in the picture, so we have kinetic energy of gluon, and we have quark-gluon vertex interaction and instantaneous gluon interaction. So other interactions, the Fock states are just absorbed into the parameters like coupling constants and mass and all these terms. And another term I talked about is the confining interaction term. So for the leading Fock sector, we took this we took the confining interaction in two terms, like two directions, transverse direction and longitudinal direction. In transverse direction, we have this from the light front holography, it is well defined. And this one is the phenomenologically introduced in the longitudinal direction. So yeah, kappa here is the confining strength in the transverse direction, and r perp here is the separation between the transverse separation between the quark and antiquark. So now to solve this Hamiltonian, we need basis function. So in the basis function in the transverse direction, we are taking two-dimensional harmonic oscillator basis, and in the longitudinal direction, we are taking the plane wave basis. In the partons basis state, the state is identified, each particle is identified by these 4 quantum numbers, and many body basis states will be identified by just, we have to take the direct product of the Fock space basis states. So now we have two truncations. First Fock state truncation, and the further one is basis truncation to limit our basis. So our main goal is to solve this light front QCD Hamiltonian. But for now, we have included only these two terms, the quark-gluon interaction term and the vertex interaction and the instantaneous gluon interaction. So to fit the parameters, we just from the spectroscopy of the light unpolarized meson mass spectrum, we just fitted our parameters. Yeah, these are our parameters to fit. Yeah, these states are taken to fit the parameters, these blue states. And yeah, we remarkably, we could identify this particle. This is the hybrid particle that cannot be identified through the the leading Fock sector. It needs gluon to be identified. So this is purely coming from the QQ bar G. Yeah, also another remarkable thing is that we could achieve the hyperfine the splitting between the pi and rho meson. So this MF here is the effective parameter. So by keeping the same other parameters same for pi and rho, we could achieve this mass splitting from this solely from this parameter, this phenomenological parameter. So yeah. So we now have produced the light front wave functions. We have light front wave functions for the rho meson. Since it is a spin-1 system, we can have SPD wave components. So these are the probabilities of different wave components of the light front wave function for the rho meson and the pion. So we are just comparing it. So for the S wave component, we found that the large contribution is coming from the second Fock sector, QQ bar G. And P wave contribution is it's comparatively low, but land it's it's comparatively low. And for the D wave, it's extremely weak. And for the pion as well, the large contribution is coming from QQ bar G sector. So the transverse momentum parton distribution functions, these provide the information about the transverse dynamics and can be accessible through CDs and the Drellian processes. These are three-dimensional functions, depends upon the longitudinal momentum and the transverse momentum of the parton. And it also provides the information about spin and orbital angular momentum. So these are some publications about the available publications for the spin-1 system, where they have few models have studied the spin-1 system in the momentum space, and there are some formalisms available. So we have now the valence quark TMDs of the spin-1 system. There are total 18 valence quark TMDs. out of which 9 are T even and 9 are T odd. So spin-1 is special because it provides the tensor structure. So there are 3 tensor polarized TMDs for T even case. And yeah, and the red ones are T odd. And these blue ones has a collinear limit, so they can produce the PDFs. So now the Gluon TMDs, we only calculated these 4 TMDs which have the collinear limit, but yeah, we are going to study all these. Basically first we will study the T even, but for now I have shown here only the 4, out of which 2 are T even, tensor polarized, and 2 are ordinary. This H1TTG is important because it provides the Gluon transversity. So these are our results for the quark TMDs of Romizon. This one is the unpolarized, this one is the helicity, and this one is the transversity for the quark case. So you see here at the low X region, there is a peak in all the distributions, particularly this. It has some little contribution. This contribution is coming from the second Fock sector, and we also observed that in the middle of the this middle distribution between x.2 and x.2 to 1, they are almost consistent with the other model results, and they have the collinear limit and are consistent with the other model results after some value of x, after x greater than 0.2 basically. And there is no interference between the different wave compositions. Like if there are the wave functions, the definitions of these TMDs are like S wave will be multiplied with S wave, P with P, overlap with P, and D will overlap with D. So there is no interference between different components. There are other TMDs like worm gear 2 TMD, worm gear 1, and pretzelocity. So these do not have the PDF limit, and their wave compositions interfere with each other. These are the important ones. This one F1LL, because it is going to be measured for the neutron case for the spin-1. So it would be interesting to see the structure of this. And this one is F1LT and F1TT. So F1LL is also do not have interference between wave compositions and has this PDF limit. And these are also consistent with other model predictions. And our distribution functions also follow the positivity constraints defined in this publication for spin-1. So now the Gluon TMDs, these are the Gluon TMDs. First, this one is unpolarized, helicity, and tensor polarized. So this one is observed to be exactly opposite to the Gluon. I mean, the magnitude is different, but the qualitative behavior is opposite to the quark F1LL. And we found in our case that this transversity Gluon TMD is 0. The reason is our weak D wave in our wave functions. So this D wave could be stronger if we include the more C quarks and the gluons in our approach. So for current approach, we found that the contribution to the spin for the rho meson from the valence quark is like 54%, and for the gluon case it's 50.2%. Now the pattern distribution functions. So these are the pattern distribution functions for quark and gluon case for the spin-1 system. So this H1TTG cannot be found for the less than spin-1 systems. So it can only be achieved for spin-1 or higher spin systems. So we also satisfy the sum rules for these PDFs. And here we compare our results for the case of Pine and rho meson just to show the difference of these two distributions for Pine and rho case in our approach for the unpolarized PDF. Yeah, for gluon, you see this is at the higher scale, like for 5.76 GeV squared. So you see the gluon is showing the expected behavior. So these are at the initial scale, all the PDFs for the gluon case at the initial scale. And this gluon, this is for the gluon case. You see this F1LL is opposite in both the cases. And these are the results for F1, this unpolarized and helicity PDF for the quark case and for the gluon case at higher scale. Yeah, this one is for the gluon, the pink one, and this shows the helicity. So we also show these moments of the PDFs. So when we compared our results with other approach like BSE and the latest QCD approach, we found that our results are a bit underestimated from this Bethe-Salpeter equation and latest QCD. So these are our predictions. Now, the BLFQ part is over. Now I want to discuss some results that we just produced last night for the neutron case. So yeah, so we are here doing this in the light front holographic QCD, where the transverse equation, transverse dynamics is defined through this light front holographic QCD wave functions, and this TUF equation describes the dynamics in the longitudinal direction. So this we have done recently. We have extended this light front holographic approach to include the longitudinal dynamics. So here we consider neutron is like 6 quark system, is exotic system, 1 quark system, 1 quark plus 5 quarks, we considered it in the spectator. So the parameters here we used like quark mass, the spectator mass, this is the confinement in the transverse direction, and this is the confinement in the longitudinal direction. So these MQ, this quark mass and G, we fixed it for the proton case to study this spectroscopy of all the hadrons basically. But for the light system, we produced this. We fitted this MQ to be 0.046 and this G to be the longitudinal confinement to be 0.109 GeV. So these are fixed. So we just changed this mass of spectator and the confinement in the transverse direction. So we fitted these parameters through this neutron mass, and we could produce this the charge form factor for the case of neutron, and these are the experimental data points. So also we could produce we could calculate the radius, charge radius, and it is comparable with the experimental data. So now we have wave functions for the neutron. We can also study the PDFs. I just wanted to show this F1LL, which is going to be measured. So yeah, this one F1L, this one is unpolarized, helicity, the transversity, and this one is a tensor polarized. Yeah, from the Hermes data, these are the data points, and this one is our, of course the scale is different. So when we increase our scale, but we don't know how to increase that scale. So if we observe this at the higher scale, then it could match with the experiment. But there is some point at the negative side, only 1 point, so we cannot conclude anything. Yeah, so we have studied the structure of rho meson through TMDs, PDFs using this light front holographic approach. And we also study, this rho meson Spin-1 system basically can provide the exotic structure, like tensor polarized structure of the system. And then we found the qualitative consistency of our results with the other model predictions. And we found that we also investigated gluon TMDs and PDFs, and we found this transversity distribution is 0, but it can be non-zero if we include more and more Fock sectors. And the other thing is we presented preliminary results on this neutron charge form factors and PDFs from extended light front holographic QCD. And our future plan is to investigate the neutron structure in BLFQ approach as well. For this, we have this eigenvalue equation for the deuteron, and yeah, where this mass will be fixed, and this is the Hamiltonian, where the interaction, this will be the sum of this kinetic energy term and the interaction term, which is the vortex, which contains the vortex interaction and instantaneous Gluon interaction, and the Fock space expansion is like 6-particle Fock sector. And if you want to study the Gluon transversity distribution, we can also study that by including another Fock sector. So yeah, thank you.
For pion and rho meson, in both cases, the subleading Fock sector is actually your dominating Fock sector, right?
Yeah.
So
That is not subleading. Yeah.
So basically, when you include gluon, right? So that component is more than your two quark anti-quark states. If you just go there.
Yeah.
Here, yes. See that QQ bar G has more than 50% contribution, right?
Yeah, because
so any intuitive way, because that is against the quark model picture, right? From quark model picture, I would expect that QQ bar will be the dominating thing and QQ bar G will be the sub.
So as we go on increasing this Fock sectors, these contributions will become lesser and lesser.
Okay, so that you say this artifact of the truncation.
Yeah.
Again.